Okay, so get ready because today we're diving headfirst into a world where, well, things can be in two places at once, the quantum realm. It's where things get really, really weird.
It's true, the quantum realm definitely keeps things interesting, that's for sure.
And speaking of interesting, you know the saying, even the best theories need a good test.
Absolutely.
Well, that's exactly what today's deep dive is all about. We're going to unpack this proposed experiment that's going after, well, one of the cornerstones of quantum mechanics as we know it.
You're talking about Born's rule, right?
That's the one. Born's rule. It's almost like, okay, imagine a coin, right? But this isn't any ordinary coin. This coin can land on heads, tails, or both at the same time, at least until you actually look at it.
Huh, I like that.
That's quantum superposition for you. And Born's rule is like I don't know, a secret code book or something. It lets us calculate the odds of each outcome when we finally DO peek at that crazy coin.
That is a great way to put it. It's like Born's rule is this bridge connecting that crazy mind-bending math of quantum mechanics to, what we see in the real world, concrete results. Like it's telling us the probability of, say, finding an electron with a very specific spin, it's tied to something called its wave function.
So it's the rule that takes all this quantum weirdness and makes it, well, measurable.
Exactly. Without Born's rule, we'd have all these crazy possibilities, but zero ways to actually predict what we're going to see when we take a measurement.
So we'd be stuck, no predictions, no understanding, just quantum chaos.
And testing Born's rule, that's what makes it so important. I mean, think about it. If it crumbled, if it were shown to be wrong, well, it wouldn't just mean changing quantum mechanics a little bit here and there. It'd mean rethinking everything we thought we knew about how the universe works at the most fundamental level.
We're talking a potential scientific revolution, no big deal. But, okay, how are these researchers planning to actually do this? I've heard whispers of lasers and something about ultra-cold atoms. What's the deal there?
Things are about to get chilly. So the experiment, it all centers around something called a Bose-Einstein Condensate. We call it a BEC for short. Basically, imagine taking a bunch of atoms and cooling them down, way, way, way down.
How cold are we talking?
We're talking crazy cold, almost to absolute zero. It's to the point where they basically, like, merge. They
Yeah.
stop acting like individual atoms and become this single quantum entity.
So instead of flipping a coin, we're talking about a giant wave of supercooled atoms. What's the advantage there?
I'll tell you what, at these ultra-low temperatures, we can essentially eliminate almost all of the random noise that you'd normally get in these quantum experiments. Imagine it's like having perfectly still water, crystal clear, for these atomic waves to just ripple through. No disturbances at all. And the BEC, it gives you incredible control over the atoms.
Okay, so I'm picturing it, but what are they actually doing with this BEC?
Well, these researchers, they're going to use lasers, high-powered lasers, to manipulate this BEC and then look for even the tiniest deviations, like really, really tiny, from what Born's rule would predict. And get this, they're even taking into account all those complicated interactions, those nonlinear interactions happening between the atoms in a BEC, which is something that past experiments have kind of struggled with.
Okay, so we've got this BEC, our super chilled super atom, just hanging out, but how do we actually use it to test Born's rule? The researchers mentioned something called an atom interferometer, which sounds, honestly, kind of complicated.
I know, right? It does sound like something straight out of Star Trek. But the idea behind it, it's actually pretty elegant when you break it down. So picture this. You've got a beam of light, and you split it in two, okay? You send those two halves down different paths. Maybe one's longer, maybe one has some kind of obstacle. Then you bring them back together, recombine them. That's your basic optical interferometer.
Okay, I'm with you so far.
And that pattern you get when you recombine them, that tells you what the light experienced on each of those paths.
Ah, I see. So, like, if one path is longer or if something messed with the light waves along the way, the pattern would be different?
You got it. Now, here's where things get really wild. Because of this whole mind-bending concept of wave-particle duality, remember, the idea that light can act like both a wave and a particle, it's a trip. I know well. It turns out we could do something similar with atoms. And that's where our atom interferometer comes in.
Hold on. So instead of splitting beams of light, they're splitting a beam of atoms. How do you even begin to do that?
Lasers, my friend. Lasers are the key to this incredibly delicate surgery.
Lasers, of course. It always comes back to lasers.
Specifically, they're using these super precise pulses from what's called a Bragg laser. Think of these pulses like, I don't know, little kicks that they can give to the atoms to make them split and travel along those different paths we were talking about within the interferometer.
So the BEC is like a perfectly synchronized marching band, and then these lasers are like those little walls that just kind of pop up and redirect the marchers into these different
I
formations.
love that analogy. You got it exactly. And it gets even cooler. They can actually use these laser pulses to block certain paths within the interferometer, essentially building a three-slit experiment, but
Yeah.
with atoms instead of light.
Wait, the three-slit experiment? Now that takes me back to high school physics. Didn't that demonstrate wave interference?
Exactly. It's a classic example of wave behavior. You shine light through three tiny slits really close together, and you get this distinct interference pattern on the screen behind them. But here's the quantum kicker. Even if you send single particles like photons, electrons, or in our case atoms, through the slits one at a time, that interference pattern, it still builds up over time.
So it's like each particle is somehow going through all three slits at the same time? What's going on there?
Right. It's like that coin we were talking about earlier, somehow landing on heads and tails simultaneously. But in this experiment, instead of using actual physical slits, the researchers are creating these blocking masks using lasers.
Okay, so the lasers are like roadblocks for the atoms.
You got it. These blocking masks, they're just carefully timed and positioned laser pulses. By controlling the momentum of the atoms with these pulses, the researchers can essentially dictate which paths the atoms can and cannot take.
So we've got our marching band. They're marching along, but now we've got these invisible laser walls guiding their every move. It's like a quantum obstacle course.
That's one way to put it. And to really fine-tune those moves, they're using what's called a Raman laser. Now, these are even cooler because instead of just giving a momentum kick Raman lasers, they mess with the atom's internal energy states, which then determines how it interacts with the other laser pulses. And that's how they control which path it follows.
Okay, that is seriously cool. But I keep hearing about this sub-recoil expansion of the BEC, and honestly, I have no idea what that means.
Good question. So it's all about the sensitivity of the experiment. Think about it. At these incredibly low temperatures, the BEC, it expands super slowly, like way slower than you'd expect based on the recoil of the atoms when they get hit by those laser pulses.
Okay.
So this subrecoil expansion, it's like giving the atoms more time,
hmm
a longer time to interact with the laser paths. And that makes the experiment much more sensitive, much more precise.
So longer interaction time equals a stronger signal, which gives them a better chance of catching any tiny deviations from Born's rule.
Exactly. It's all about maximizing that signal-to-noise ratio. And that brings us to, I think, the most exciting part.
Yeah.
How do we measure what's actually happening in this experiment? And how do we know if Born's rule is holding up or not?
Okay, let's break it down. We've got these atoms, they're marching along, splitting up, taking different paths. Some are even hitting those laser roadblocks you were talking about. What happens at the end of all this? What are we actually looking at to see if Born's rule is, holding true?
Well, it all comes down to the interference pattern.
hmm
Remember how we were talking about that with the three-slit experiment?
Yeah.
So Born's rule, it predicts a very specific pattern based on the probabilities of each atom taking a particular path. Think of it like this. If blocking one path, it leads to a result that, well, that can't be explained just by adding up the probabilities of the other paths, then things start to get really interesting.
Interesting how, what would that even mean?
It would mean that our understanding of how quantum probabilities work, well, it might be incomplete.
Okay, I think I'm following. So it's like if a few of our marching band members suddenly ended up in formations that, well, they shouldn't be able to reach given the paths they could take, that would be a problem, right?
Exactly. Like, how did they get there?
Yeah.
And to measure these deviations, these, I guess you could call them rule-breaking moments, that's where the Sorkin parameter comes in.
The Sorkin parameter. Another one for the quantum glossary.
Right. It sounds complicated, but really just think of it like a, I don't know, a barometer for how quantum the results are. A higher Sorkin parameter, it means the experiment is showing us something that just can't be explained by classical physics, something fundamentally strange.
So a high Sorkin parameter equals a potential crack in the foundation of, well, everything we thought we knew about quantum mechanics.
You got it. And one of the things that's so impressive about this proposal, it's how these researchers are accounting for potential errors. I mean, they're really trying to cover all their bases. They're running these incredibly detailed simulations, and they're factoring in things like how accurate are the laser pulses, what's the uncertainty in measuring the atom's positions, and even those nonlinear interactions within the BEC itself.
So they're making absolutely sure that, to use our analogy, if their marching band goes off script, it's not because, someone tripped over a laser beam or something. It's because of actual quantum weirdness.
Exactly. And their simulations, well, they're showing that they can reach this incredible level of sensitivity, like unprecedented levels, really. We're talking about potentially detecting deviations from Born's rule that are so small, so tiny, that previous experiments wouldn't have even been able to notice them.
That's pretty amazing. But okay, let's say everything goes perfectly okay. They get their results and everything lines up with Bourne's rule exactly. Does that mean this whole experiment was like a waste?
Not at all. Even confirming Born's rule with this level of precision, that would be a huge accomplishment in itself. It would mean that this core principle of quantum mechanics, this bedrock idea, it would mean it passed one of the most rigorous tests we can throw at it.
So it's less about breaking quantum mechanics and more about like fine-tuning our understanding of it.
Exactly. It's like, yeah, quantum mechanics, it's still super weird, but we're getting a better handle on all those quirks, you know?
And who doesn't love a good quantum quirk?
Right. And plus, the technology itself, the techniques that they're developing for this experiment, those have huge implications for other areas of physics. I mean, we could see breakthroughs in quantum computing, in ultra-precise sensors. Who knows what the future holds?
It's a win-win, even if they don't completely upend our understanding of physics. But you know me, I love a good what if. So, what if they do find a deviation from Bourne's rule? Then what? What would that tell us about, the universe, reality, all that big stuff?
That's the million-dollar question, isn't it?
Yeah.
Well, it could suggest that there's something even deeper going on, something beneath quantum mechanics as we know it, something we haven't even begun to imagine.
Deeper than quantum mechanics, that's a lot of depth.
Right. Our whole concept of probability. It might need a serious rethink. And who knows, maybe the universe is even weirder than we thought.
It's like we've been listening to this symphony, this quantum symphony, and we thought we knew all the instruments, all the notes, but then suddenly we hear this completely new sound, something unexpected. It makes you realize there's a whole other layer of music, a whole other part of the orchestra that we never even knew existed.
That's a great way to put it. And it really highlights how much we still don't know about the quantum world.
Well, there you have it. A mind-blowing experiment that could potentially rewrite the rules of quantum mechanics. Or, at the very least, it's going to give us an even deeper appreciation for just how elegant, how strange, how utterly mind-boggling this quantum realm really is. Hey, if you learned anything from today's deep dive, I hope it's that even when we think we've figured things out, even with our most well-established theories, there's always more to discover, more to question, and a whole lot more to marvel at in this vast, incredible universe. Thanks for listening.